Spectroscopic or optical analyzers measure and identify selected components in a process sample based on each component's interaction with light. The interaction between light and the process sample may be characterized as absorption, luminescence, emission, or refraction. For the purpose of this program, only absorption will be discussed. Spectroscopic analyzers respond to ultraviolet, visible, or infrared light and can be configured to measure a wide range of either gas or liquid components. They provide continuous analysis of the process, so reaction to the target component is instantaneous. Spectroscopic analyzers are considered rugged and more reliable than some other types of analyzers because they have few or no moving parts. This factor also makes spectroscopic analyzers easier to maintain. The typical spectroscopic analyzer consists of at least 5 basic elements, plus a power supply and control station. Radiation from a light source passes through the filter, which blocks all light except a reference wavelength and a measurement wavelength. The reference wavelength is not absorbed by the sample component of interest, while the measurement wavelength is absorbed. The reference wavelength compensates for any contamination in the optical path, such as sample cell window fogging. As a conditioned process sample flows through the sample cell, it enters the optical path, where it absorbs a specific amount of the measurement wavelength based on the sample's molecular structure. The detector senses the amount of measurement wavelength radiation not absorbed by the process sample. It then compares the reference and measurement wavelengths to identify the sample. The detector transduces the results of this comparison into an electrical signal. The electronics section of the analyzer translates the detector signal into an output usable by other process control equipment and personnel. The control station can be operated manually or automatically. In either case, it is used for zero and span settings and for maintenance and test functions. The control station can be mounted remotely in a control room or adjacent to the analyzer in a protective housing, as long as it meets area safety requirements. The power supply provides regulated voltage to the analyzer. It may be a separate component or an integral part of the analyzer or controller. Spectroscopic analyzers are often configured to measure a single process component. However, some analyzers can measure multiple components by scanning at various wavelengths and measuring absorption at those wavelengths. Other factors such as cell length and detector type are selected to be appropriate for each component and concentration level that's to be measured. The elements of the spectroscopic analyzer can be arranged in a variety of ways. With each configuration, both measurement and reference wavelengths of radiation are necessary for analysis. Single beam analyzers compare the energy levels of 2 or more wavelengths. Measurement and reference filters are mounted on a motor-driven filter wheel. As the wheel rotates, radiation at the measurement and reference wavelengths alternately pass through the sample cell to the detector. The measurement wavelength is absorbed, while the reference wavelength is unaffected by the sample. The detector responds to the differences in energy levels of each wavelength and generates a concentration reading. Dual beam analyzers contain a sample cell and a reference cell. One beam passes through a motor-driven chopper wheel, a stationary measurement filter, and the sample cell, then strikes the detector. The second beam passes through the chopper and filter, then through the reference cell. The reference cell contains a gas that is optically similar to the background. When the analyte enters the sample cell, it absorbs energy from the measurement beam. The detector responds to the difference in energy levels between the beams and generates a concentration reading. Split beam analyzers compare the energy levels at 2 different wavelengths. A beam of radiation passes through a sample cell where some of its energy is absorbed. It then strikes a beam splitter. One resulting beam containing multiple wavelengths passes through an optical filter, which allows only the measurement wavelength through to the detector. The reflected beam strikes a second filter, which passes only the reference wavelength to a second detector. Analyzer electronics compare detector signals to determine how much energy the analyte has absorbed. This generates a concentration reading. Single-beam open-path analyzers measure concentrations of contaminants in ambient air. They are commonly used to analyze process emissions from smokestacks. This is known as across-the-stack monitoring. It's difficult to calibrate this type of analyzer because the smokestack acts as the sample cell, and it cannot be filled with calibration sample. Instead, filters are often used for calibration, but they may lack reliability. In this example, the analyzer consists of a source and receiver that are located on opposite sides of the area to be monitored. Contaminants moving between the source and receiver absorb energy. The energy absorbed by the contaminants is measured in the receiver. Another type of infrared open-path analyzer measures film coating thickness. A source beam is reflected down to and back from the film. Variations in reflected beam intensity are proportional to coating thickness. In the next segment, you'll learn about source maintenance. But for now, review the material we just covered in your workbook. Before beginning spectroscopic analyzer source inspection and maintenance, there are some precautions that you should take. Familiarize yourself with the manufacturer's safety guidelines for the analyzer with which you're working. Also, be familiar with your facility's safety guidelines, which may include special procedures for handling toxic or dangerous substances. Most newer analyzers may have self-diagnostics software that can greatly aid troubleshooting efforts by isolating the fault to the source, cell, detector, or the electronics portions of the analyzer. Consult the manufacturer's manual for further information about your specific analyzer. It's important to remember that the light source of an ultraviolet analyzer emits radiation, which is dangerous to the eyes and skin. Wear protective eyewear and clothing and avoid direct exposure to the light source. Always disconnect the analyzer from all power sources before beginning any corrective maintenance. Various elements of the analyzer may have separate power sources, so be certain to check for separate electrical connections to the chopper motor, cell heater, and other elements in the analyzer system. Test to ensure that all power sources are disconnected. The source may generate high temperatures during operation. Let the source cool before beginning maintenance. Keep in mind that many process samples, gas and liquid streams, and test samples are toxic. They may also be asphyxiates, corrosive, flammable, or a combination of these. The analyzer should be vented according to your facility's guidelines and manufacturer's recommendations. All sample pressure indicators should be checked before any tests or maintenance to ensure that there are no leaks and that the sample cell is free of gas and process sample. Avoid direct contact with dangerous cleaning solutions and use the proper eye and skin protection as required. In some cases, respiratory protection may also be required. The chemicals and cleaning solutions that you use should be those recommended by the analyzer manufacturer and approved for use in your facility. Various analyzer elements require special cleaning procedures. Avoid using abrasive cleaning solutions and materials on cell windows, lenses, or mirrors, and be certain that other analyzer elements will not be damaged by the cleaning solution. All used cleaning materials, solvents, and empty containers should be disposed of according to government regulations and your facility's specifications. Analyzer source problems may become evident in a variety of ways. A faulty source may cause baseline drift or erratic output, or the analyzer may not differentiate or respond to the sample component of interest. A source problem is suspected for this split beam analyzer. First, check that the lamp is operating properly. Ensure that the analyzer power is on, and check the output. Check the reference and measure channels. If both channels read 0, check lamp operation by removing the cell housing cover. Avoid looking in the direction of the source. When working around ultraviolet light sources, be certain to use proper eye and skin protection. If there is no source lamp reflection, power may not be reaching the lamp. The analyzer may have a blown fuse or tripped circuit breaker. Check for voltage through the fuse or breaker. If the fuse is blown, ensure power is turned off and replace the fuse. If the fuse blows again, further troubleshooting efforts will be required. This analyzer is equipped with a combination ballast and lamp transformer. If the output voltage is not correct, you'll need to de-energize the analyzer and isolate the faulty component by taking resistance readings to determine if the problem is with the transformer or the ballast. Replace the ballast if it's found to be faulty. If the transformer is the source of the problem, replace it. Source failure may also be caused by a faulty power supply transformer or voltage regulator. Check for proper voltage at the power supply board. If the proper voltage is not present, replace the voltage regulator. If the power supply components are operating properly, then you'll need to de-energize the analyzer and replace the lamp. Remove the lamp cover and carefully remove the old source lamp. Replace the lamp with one approved by the manufacturer for use in your analyzer. Oils or grease can shorten the lamp's life. Even oils from your fingers can affect its operation. If any oils or grease accumulate on the lamp, try cleaning it or obtain a new bulb. You should also ensure that the lamp shields are grounded according to the manufacturer's guidelines. Turn on the analyzer. If the bulb illuminates, give it time to stabilize before calibration. Calibration is discussed later in this program. To replace an infrared or visible light analyzer lamp, first de-energize the analyzer and wait until the lamp assembly cools. Remove the lamp housing cover. Unplug and remove the lamp assembly. The replacement lamp should be selected according to manufacturer's specifications and the analysis requirements. Replacement lamp installation is usually the reverse of lamp removal. In some analyzers, other elements of the lamp assembly may need to be removed, such as the lamp shield or housing cover, to replace the lamp. These elements don't need to be replaced unless there are signs of damage. There are usually no special procedures for restarting the lamp, other than simply turning on power to the analyzer and allowing it to stabilize. Consult the manufacturer's guidelines to determine how long this will take. In the next segment, you'll learn about optical path maintenance. But for now, review the material we just covered in your workbook. A spectroscopic analyzer optical path usually contains the following devices: a sample cell, the type and style depending on the analyzer light source and the process analyte, measurement and reference filters, lenses, and detector. Some spectroscopic analyzers might also contain beam splitters and mirrors, or a chopper wheel and motor. Spectroscopic analyzer filters usually require very little maintenance because they filter only light. No process components come into contact with them. Be sure the filters are clean following maintenance of other analyzer elements. Avoid getting the mirrors and lenses dirty. When the analyzer cover is removed for maintenance, check for dust, fingerprints, or excess cleaning solution. Clean the lenses as necessary. Sometimes the chopper wheel motor can fail or go out of sync. Problems caused by chopper wheel motor failure may be indicated by an incorrect or lack of response from the analyzer. If the motor has failed, replace it. First, de-energize the analyzer, then disconnect the signal connections. For this analyzer, remove the chopper motor module. Remove any screws or brackets securing the failed motor and lift the motor out of the analyzer. Install a replacement module according to the manufacturer's instructions. Realign the chopper wheel module and reconnect the signal wires. If the motor still does not operate, troubleshoot the motor control circuit. Refer to the manufacturer's instructions for procedures specific to your analyzer. If the motor is out of sync, adjust it according to manufacturer's instructions. Sample cell construction varies according to manufacturer and process specifications. The following demonstration shows some typical procedures for a single beam infrared analyzer. Symptoms of a dirty sample cell are low gain, erratic output, or drift. Some cells are heated, and if the heater control is faulty, it can cause drift. Prior to beginning maintenance, thoroughly flush the sample cell with nitrogen to purge the cell of samples that may be toxic. This is best accomplished by using the zero or reference gas for a predetermined period of time. Proof of flow may be observed by watching rotometer flow drop and return to previously set flow as the sample system is changed from process gas to reference gas. Some analyzers, for example CO and CO2 analyzers, have a nitrogen purge to keep ambient air out of the optical path. Other analyzers, like this one, use chemical scrubbers to remove the CO and CO2. If there are purge connections fitted to the flanges, remove them. Try flushing the sample cell before dismantling it for routine cleaning and maintenance. Dismantling the sample cell increases the chances of breaking the sample cell windows and results in longer downtime. With the sample cell in the analyzer, disconnect the process connections. Flush the sample cell with a cleansing solution, such as isopropyl alcohol or methanol. Ensure that the cleanser is compatible with the cell windows and window coatings. The cleanser should also be compatible with the process stream in case there are traces left in the sample cell. Carefully check the solution as it's washed out of the sample cell. If no contaminant washes out, try the procedure with a different cleansing solution. After flushing, purge the sample cell with air or nitrogen. If the sample cell is still dirty after purging, disassembly is necessary, and you'll need to remove the cell from the analyzer. If the analyzer cell is heated, disconnect the heating element. Be careful not to pull or strain heater connection leads at any stage of cell assembly removal. If your analyzer is equipped with a thermocouple, carefully disconnect and remove it from the cell body. Loosen the screws holding the cell flanges at either end of the sample cell. While supporting the cell assembly, pull the flanges inward from the cell ends. It may also be necessary to loosen the screws holding the source end onto the mounting chassis. Now, remove the cell assembly. Take the entire cell assembly to a clean, dry area where it can be safely dismantled. Remove the gas scrubbers from the flanges and pull the flanges off the cell body. Then remove the protective cover and heating elements if installed. Before the cell windows can be removed and cleaned, some precautions should be noted. Cell windows are often high-grade single crystal material. They may also have special coatings that make them very fragile. The window coatings for some applications may include germanium, barium fluoride, or zinc selenide, which are toxic. See the specifications for the application you're working with and handle any toxic coatings according to your facility's guidelines. Cotton gloves or finger cots should be worn when handling the cell windows. Begin cell window removal by ensuring that the flanges have been removed from the cell body. Remove the necessary hardware to access the window. The following procedure will help avoid window damage. Seal the outlet and hold the cell so that the window will not drop out. Connect a hand-operated aspirator to the inlet. Apply gentle pressure to lift the window up squarely and remove it. Now, remove the window gaskets. Dismantle the other end of the cell in the same manner. Inspect the windows for chips, cracks, and etching. Now, clean the cell components. First, change gloves to a chemical-resistant glove and clean the cell windows with lens tissue or a soft towel and a detergent or solvent such as isopropanol. Do not use abrasive cleaning compounds which may damage the optical surface. Clean the inside of the cell body with an approved cleaning solution and brush. Ensure that all deposits are removed. Some sample cells have highly polished or gold-plated inner surfaces that should be cleaned as recommended by the manufacturer. Rinse or flush the cell with distilled or deionized water to remove any residual cleaning solution and set the parts aside to dry. The reassembly process is the reverse of the dismantling process, with some exceptions. Thin cotton or rubber gloves should be used to prevent contamination of components and to provide dexterity for handling small parts. Insert new gaskets and carefully replace the windows. Install new O-rings and other sealing kit items. Ensure that all pieces are free of dust, hairs, or particles that may adversely affect the analyzer. At this point, you should also recheck the windows to ensure that they are free of solvents, residues, and fingerprints. The locking ring threads should be lightly coated with a suitable lubricant. Be sure to wipe off any excess. Tighten the ring gradually, pausing to allow the gasket to seat. Continue this process until the metal faces of the locking ring and cell body meet. Be certain that they are fully tight and there is no gap between them. If the O-rings are Teflon, greater torque and longer pauses will be necessary because Teflon is not as pliable as rubber. To avoid cell damage, do not use the cell inlet or outlet stubs as levers as you tighten the locking ring. After the cell is reassembled, conduct a leak check to ensure that process sample will not leak out and damage other analyzer elements. First, cap off the sample cell inlet. Connect an air pressure source to the cell outlet. The connection should be sealed tightly. Apply moderate air pressure. Be sure not to exceed the pressure tolerance of the cell. Then, submerge the sample cell into a container of water or spray the cell with leak detector. If there are no leaks, the sample cell is ready for final reassembly. Dry the sample cell with a towel and remove the test equipment. If a leak check solution was used, be sure to clean the cell windows of any residual solution. After the outlet cover and flanges have been reinstalled, the sample cell assembly is ready to be reinstalled in the analyzer. Reinstallation is the reverse of the dismantling process. Be sure mating surfaces are clean and install new dry O-rings. Place the cell assembly into the analyzer chassis and install one screw on either side to support the cell. Spread the flanges to seat properly and install the remaining mounting hardware. Be sure to fully tighten the screws holding the source end onto the mounting chassis. After the cell has been mounted, flush the flanges with clean, dry nitrogen. Then, new absorbent scrubbers should be quickly screwed into place. Some analyzers may have an alignment procedure to correctly position the sample cell. Follow the manufacturer's instructions for your analyzer. After the cell assembly is securely fastened into the analyzer, insert the thermocouple in the cell body and tighten the retaining nut. Reconnect the process connections. Pressurize the cell with reference gas and conduct a leak check of process fittings to ensure no leakage. Now, restore process flow and turn on the analyzer. In the next segment, you'll learn routine maintenance and calibration of spectroscopic analyzers. But for now, review the material we just covered in your workbook. Routine spectroscopic analyzer maintenance will help ensure consistent and accurate readings for any application. Use the maintenance schedule provided by the manufacturer and adjust it to meet the specific maintenance needs of your analyzer and process. One key to maintenance is sample conditioning. It's critical that the sample conditioning system supplies a representative sample and removes undesirable particulates and condensates before they reach the analyzer. Filters should be changed on a regular or periodic basis, or if there is a marked decrease in sample flow. To remove the filter, block sample flow by turning off the sample inlet valve, shutting the analyzer valve and the sample return or vent valve, and bleeding off any residual pressure. Remove the old filter and replace as necessary. Be sure to use a filter that is specifically designed for your system. The sample conditioning system also maintains sample pressure. Spectroscopic analyzers, more than other analyzers, require stable pressure in the sample cell since pressure affects the number of molecules in the sample cell. Pressure regulators may also be used in the process line to reduce process pressure to a safe working pressure for the sample system and the analyzer cell. Use of a pressure regulator can also provide a faster sample transport time. Check the pressure gauges and flow meters to ensure proper operation. Ensure that there are no leaks and that all fittings are secure throughout the sample conditioning system. Check for the proper temperature of the sample system and the analyzer. In some process environments, you may need to inspect analyzer components for corrosion or deterioration. A corrosive atmosphere can have detrimental effects on the analyzer. Ensure power is turned off and allow the source to cool. Ensure the surrounding atmosphere is non-corrosive before you remove the analyzer cover. Check for corrosion or other damage to wiring, tubing, optical filters, sample cell, lamp and mounting, and the amplifier unit. Check the electronics board wiring and plugs. Ensure that the amplifier is properly grounded. Check the sample cell for evidence of leaks and check the cell windows for cleanliness. Repair any leaks and clean the cell windows as necessary. If your analyzer is heated, check for evidence of overheating. If your analyzer is steam heated, check for leaks and make repairs as necessary. Check the wiring and connections on the power supply unit and control station. Repair or replace any damaged or corroded parts. Turn on power to the analyzer. The analyzer should be calibrated on a periodic basis and after maintenance. Since process changes, environmental changes, or element aging can cause analyzer readings to drift, it's important to check whether the readings are still valid. These checks include zeroing the analyzer and adjusting the span. For this analyzer, sample pump flow is checked to ensure the proper amount of sample is drawn into the sample cell. To zero the analyzer, introduce a sample of known concentration that is transparent at the wavelength of interest. It can contain either a mix of pure components or the average background stream without the analyte of interest. In either case, calibration samples can be bottled samples which have been certified as accurate or validated in the plant lab. Introducing the zeroing sample should produce a zero concentration reading at the analyzer readout. To check span, add a known concentration of the analyte of interest to the zeroing gas and take a reading. The reading should match the known concentration. If it does not, adjust the span as necessary. In some analyzers, a calibration filter simulates the span sample. However, the sample cell should be emptied and purged in preparation for this procedure. After calibration, restore the analyzer to service and record the calibration results in accordance with your facility guidelines. ISA's Instrument Technology Training Program is general in nature. When performing instrumentation maintenance in your plant, be sure to follow the specific maintenance and safety procedures